Third keynote speaker is Dr. Carisa Harris-Adamson. Dr. Harris is an associate professor to the Department of Medicine at the University of California at San Francisco. She's a director of the Northern California Center of Occupational and Environmental Health at the University of California, Berkeley, an associate director of research for the California Labor Lab, which is a NIOSH Total Worker Health Center, and a director for the UC San Francisco and UC Berkeley Ergonomics Research and Graduate Training Program. Dr. Harris and her team performs research in a variety of areas focused on understanding and preventing work-related injuries and improving human performance, productivity, and health. Dr. Harris's presentation is entitled Evaluation of Exoskeletons for Construction. And with that, we'll begin the presentation.
Welcome to an overview of our project evaluating exoskeletons for construction. This work is supported by CPWR and includes researchers from the University of California, San Francisco, UC Berkeley, and Virginia Tech. My name is Dr. Carisa Harris, and I'm the director of the UC Ergonomics Research and Graduate Training Program. I'd like to acknowledge my colleagues who have also been working on this project. I have no personal financial conflicts of interest to disclose, but my program is supported by these companies. So construction workers continue to experience high rates of work-related musculoskeletal disorders and have higher injury rates than other industry sectors. The back and the shoulder are the most impacted body regions, with the back injuries accounting for 43% of all cases, and shoulder injuries have a median of 25 lost work days. Overall, there are 4 aims included in this 5-year project. The first aim of this project is to obtain input from construction industry stakeholders, while our second aim is to determine the efficacy of exoskeletons. The third aim is to assess the perceived safety, effectiveness, and acceptability of exoskeletons in construction. And our fourth aim will be to disseminate the study findings nationwide. Today, I'm going to provide an overview of the work done to support Aim 1 and Aim 2. So the first aim was to gather input from stakeholders. We presented an introductory video about exoskeletons and then administered an online survey with 70 open and close-ended questions. We collected input from 361 construction workers, 63% of whom were Caucasian and 24% of whom were Hispanic. 77% of the respondents were male, with a median age of 47 years. 66% of respondents had more than 15 years of work experience in companies of various sizes. 36% had heard of workers using an exoskeleton, while 35% had never heard of it at all. When asked about discomfort in the shoulder and back due to construction work, nearly a third of respondents reported moderate to severe shoulder pain, with an equal amount reporting moderate to severe back pain. We had 4 exoskeleton receptivity scales, including the benefits of exoskeletons, the barriers of exoskeletons, perceptions of exoskeletons, and workers' readiness to use. There were 3 to 4 questions that were used to assess each of these different perceptions of exoskeleton use. Then responses to each question were scored and added together to get 1 cumulative score for each of these scales. Now in the upper right-hand corner, you can see the distribution of physical fatigue at the end of a workday in orange and in the work week in blue. As you can see, most people reported fatigue between 7 and 8 on a 10-point scale. We then looked at comparing different receptivity scores by the level of reported fatigue to see if those with more fatigue at the end of their workday or work week had different perceptions on benefits, barriers, and readiness to use. We found that those with extreme fatigue at the end of their workday or work week reported a more positive reception to exoskeletons, higher benefits of exoskeletons, and more readiness to use than those with lower fatigue. The potential barriers of exoskeleton use was fairly similar across those experiencing different levels of fatigue. Also of interest was the findings on fitting and sharing exoskeletons. Although 97% of workers agreed that they would share an exoskeleton, 80% also agreed that it would be difficult to refit or use. Other barriers to use included safety concerns, such as the impact of exoskeletons on slip, trip, falls, or being able to get out of harm's way. This particular finding impacted further research that we did in AIM 2. To address one of the concerns identified from the stakeholder survey, we developed a tool to predict proper anthropometric fit and support levels of arm support exoskeletons that would make it easier for workers to adjust the exoskeleton and fit them, as well as adjust the support levels to meet the demands of different tasks. Increasing the ease of exoskeleton fitting and adjustments would improve the usability by allowing smaller size construction companies to fit arm support exoskeletons without an expert present, allow employees to share and readjust with proper fit, and allow the support level to be readjusted based on task demands. So we developed prediction equations that only require a person's height, weight, and sex that provides the exoskeleton specific settings, which were then validated using an exoskeleton researcher to assume proper fit. Here's an example for one specific arm support exoskeleton. Using the Answer anthropometric database, we estimated spine height from the person's height. A linear fit was then established between the available arm support exoskeleton settings and body dimension. After estimating the body dimension, the corresponding available setting was chosen. Settings were, of course, rounded to the nearest whole number based on what was available in this exoskeleton. This was repeated for each setting that was available on this specific arm support exoskeleton, including predicted shoulder breadth and predicted arm length settings. Next, to predict the optimal support setting to achieve a fully supported arm at 90 degrees of shoulder flexion, we used a force gauge and long arm protractor with the arm support exoskeleton shoulder joint at 90 degrees of shoulder flexion and 90 degrees of elbow flexion to measure the reaction force provided at each setting and for each arm cuff length. Using the person's weight, we then predicted the proper setting to achieve a floating arm with the person's upper extremity at this 90-90 position, which you can see in this slide here. So using the manufacturer's recommendations, we then identified definitions for specific anthropometric fit that was specific to each arm support exoskeleton. For example, for this exoskeleton, a proper shoulder breadth prediction required a small gap to be between the shoulder and the arm unit. A proper arm length prediction required the arm cuff to be aligned with the end of the elbow when the shoulder and elbow were in the 90-90 position. A proper spine length prediction required that there be no contact between the upper shoulder frame and the top of the user's shoulder during their entire range of motion. It also required that the hip pads be over the hip bones and the spine unit to be vertical along the spine. So we then looked at the percent of good predictions for each of the settings predicted. This table includes the validation from 15 individuals. As you can see, for each anthropometric fit predicted, including shoulder breadth, spine length, and arm length, the number of good predictions ranged between 53 and 87%, with a total positive prediction of 73%. Arm length had the lowest number of good predictions at 53%, which has led us to go back and modify our equations and adjust them slightly. The support level had the highest number of good predictions, with 14 out of 15 participants correctly predicting the support level to float their arm according to the manufacturer's recommendations. Interestingly, there were differences by sex. Females had 30% fewer good prediction in anthropometric settings, with the arm length settings among women having the lowest prediction of all. This work is ongoing and will include as many arm support exoskeletons as possible that are commercially available. Our next step is to refine the predictive equations for each exoskeleton and to determine how support level might change based on different task characteristics. And that brings us to aim 2. As part of aim 2, we will determine the efficacy of commercially available arm support and back support exoskeletons by investigating the effects of various arm support levels and task characteristics such as precision and posture of the task. We'll look at safety, functional performance, physical demands, work performance, and usability. This work is ongoing, wherein we've been investigating the impact of exoskeleton use on maneuverability, balance, gait, and specific tasks like shoveling and climbing using different exoskeletons that vary in design characteristics, as well as looking at the impact of fall harnesses and tool belts while being worn with the exoskeleton. In this experiment, the support level has been fixed to floating the arm in the 90-90 arm position. You can see that participants move through a safety obstacle course that requires moving through confined spaces, navigating ladders, walking on beams, balancing on frames, and stepping down onto a force plate. The obstacle course includes common safety challenges observed in a construction environment. Our dependent variables include time to completion, number of errors, that includes snags, bumps, and any contact made. And we're also looking at body kinematics and user perception, such as perceived exertion, comfort, discomfort, safety, and usability. To identify optimal support settings from the exoskeleton based on different task characteristics, we have a variety of tasks that vary the location of the work being done, either overhead or on the wall. We also will vary the type of work, which could be static or sustained, both overhead and on the wall. This assumes that static means that the arms are overhead and remaining overhead, whereas dynamic work means that they are constantly moving their arm maybe up overhead and then back towards the side of their body. We're testing 4 support levels: no support, low support, medium support, and high support. The levels of support correspond to a certain percent of the person's arm weight. Additionally, we will compare comfort and preference across exoskeleton design characteristics when they're performing these various tasks. Virginia Tech is looking at the back support exoskeletons, and they're also doing a safety test, looking at tasks like donning and doffing, 3-point kneeling, squatting, stair climbing, and their conditions include no exoskeleton, the back X, the Pexo back, hero wear, and apex. And you can see from this diagram the various tasks that are being tested in their safety obstacle course, including things like the figure 8 walking, the ladder climb, scaffolding, stud wall walk, window walk, beam balance, shoveling, a ramp walk, and a low ceiling crawl. Their dependent measures are also things like time to completion and user perceptions on physical exertion, discomfort, movement restrictions, task interference, balance, and safety. For the box stacking task, low ceiling crawl, and scaffold climbing, all back support exoskeletons required increased time for task completion compared to not wearing a back support exoskeleton. The back X and hero wear also required more time to complete the shoveling task. There were minimal differences across conditions during the window walk and stud wall task. This preliminary data also shows that despite increased time to complete a task, the perceived physical effort only increased across 3 BSEs while shoveling. The Pexo back increased perceived effort while climbing the scaffolding and window walking, while the hero wear decreased perceived effort during the window walk. Overall, there were limited effects of the exoskeleton on perceived discomfort while performing the various tasks. Once we complete the work described, we will also be assessing exoskeleton use while performing specific tasks, including concrete grinding and drywall installation when using an arm support exoskeleton, and roofing and tiling when using the back support exoskeleton. We look forward to sharing these results in the upcoming year. And thank you for your time and attention. And once again, I'd like to acknowledge NIOSH and CPWR for their support of this project.